Thank you for inviting me to come and speak. I'm going to talk about PRISM signal processing and the importance of validation in measurement for the Internet of Things. So, I'd like to start by acknowledging my colleagues at Oxford University and also my colleagues... Nope? Okay. How's that? Stereo. Okay. I'd like to also acknowledge my colleagues here in Southern Ural State University, particularly Oleg Bushev and Vladimir Sinitsyn, whose work I will be using in the course of this presentation. But all the colleagues here in Southern Ural State University, we have a very fruitful collaboration together. Okay, so what I'm going to talk about is the Internet of Things, which is of course the subject of this conference, and the metrology challenges, the particular measurement challenges that arise from the Internet of Things. And then I will talk briefly on the general idea of PRISM signal processing, which is a response to that, those challenges. I'll describe some new developments that have occurred in the last few months about bandpass filtering and PRISM spectra that is a further contribution to the requirements for the Internet of Things. And then I'll talk about two applications very briefly, both developed here. One is pressure sensor monitoring, and the other is condition monitoring for rotating machinery. Okay. So we'll start by looking at the Internet of Things and the metrology challenges, the measurement challenges associated with the Internet of Things. Okay, so we've heard this morning and we heard yesterday all about the wonders, the joys, the potentials, the opportunities of the Internet of Things and Industry 4.0. And of course, there are many potential benefits. And again, we heard this morning about the opportunities in the energy sector, in manufacturing, in homes, in health, many areas where we can do things in a new way, and there's a potential for efficiency and improved functionality in the delivery of systems and services throughout the world. But this new approach places great demands on sensors and measurement. So the challenge from a measurement point of view is that we have many new devices, often with specialized sensing technology. Greater flexibility and functionality is required. But because so many new devices are being produced, there is less design expertise available as a new product is developed. So it's actually harder to develop sensors as more are needed. Systems are becoming increasingly reliant upon sensor data, but then how do we validate sensor information? And we heard this morning the challenge of uncertainty at higher levels, but the uncertainty of the measurement data being generated at the bottom is a very, very difficult problem. And so how do we validate the sensor information? Now, in St. Petersburg, there is a great man called Taimanov, who is a long-standing friend and colleague of mine and of SUSU. And he said this in a paper just last year, that the Internet of Things poses new tasks for metrology specialists. And without solving these tasks, solving these problems, the coming era could bring more dangers than hopes. So, billions of sensors, generating data, how do we trust it, how do we interpret it? That is the challenge to measurement from the Internet of Things. Okay. Now, again, we've heard about uncertainty. Well, here's another definition of uncertainty. There's a concept of metrological self-check, or a self-validating sensor, which has been discussed and standardized over the last decades. And the idea is that the sensor itself performs self-checking inside of itself, and if it detects a fault, instead of simply giving you the faulty data with an error code, hey, I've got a problem, the device corrects itself as far as it can, but also provides an uncertainty estimate of the measurement data that it is generating. So in this example here, this is data generated from a data generated from a Coriolis meter, a mass flow meter. We have the measurement is fine up to this point, and at this point a fault occurs, and the raw measurement is faulty, and so there's an error in it. But what the device does is instead of generating this, let's go back. Instead of generating this false data and just supplying it and say, hey, I've got an error, some kind of error code, it corrects the measurement internally to provide a corrected measurement, but also it provides an uncertainty band saying how good the measurement data is. So before the fault we have a very small uncertainty here, but then we have a broader uncertainty as in the faulty condition. So high-level systems can adapt to the quality of the measurement data even though a fault has occurred. And so this is a general idea for measurement validation that has been developed over the years. Coming back to here now. So let me see, wrong way. So standards defining this have been developed over the years. In the UK, this came out in 2001. In Russia, it came out in 2011. I was involved in the British standard. Taimanov was involved in the Russian standard. Great ideas, it isn't used. Okay, it's difficult. And indeed, the problem is made worse precisely because of the Internet of Things challenge. Doing that validation is harder than doing just the basic measurement. And so we need yet more expertise, yet more computing power. And so in addition to, now one way of dealing with this is to do system level solutions like deep learning and so on. But we also need new signal processing techniques down in the sensor itself to allow us to do more measurement, flexible measurement, and measurement validation. So that's where this PRISM signal processing comes in. And this is a technique we've been developing at Oxford for a couple of years now, and we think it provides a valuable solution to part of this problem. Okay, so what is a PRISM? A PRISM is a new type of signal processing software module. I'll show you the structure in the next slide. The key point is that it is extremely fast, it is extremely flexible, and it has instant design so that you can create new networks in real time to solve problems as they emerge. The structure looks like this. The mathematics, well, it looks more complicated than it is. Essentially, it's a cascade of Fourier integrals. And it has two parameters, the frequency and what's called the harmonic number. And unlike a conventional filter where you have to do the filter design, which itself is a big computation, because this has a Fourier style of structure, the coefficients are just sine and cosine values, and so it can be created instantly. Now, I've given talks here before about PRISM, and there are many things that you can do with it in terms of conventional filtering and tracking of signals and so on. I'll just describe here a new technique developed over the last few months, which will give you a flavour of what this thing can do. So, if we want to create a bandpass filter to process measurement data, we can use a series of prisms to do this. So here, where are we? If we put, this is the frequency response of various types of prism. This is a linear scale, this is a logarithmic scale. And they have these characteristic regular notches. But we can string a few of these together to create a bandpass filter, simply by selecting the parameter values so that the peaks line up. And so that's just two there. You can see here, we start to put a few more together and we can see a bandpass filter being formed here. And over here, this is a computed example where this is the blue is the theoretical curve, the green is the filtered result on white noise. So this is starting to look like a decent bandpass filter. But we can generalize this to form a generic PRISM filter design where if you put six prisms together, you can produce a bandpass filter with arbitrarily narrow bandpass, as you will see, where the design is instant. So this can be created in real time in any compute device anywhere, instantly. Given your desire for the central frequency and your bandpass, very simple calculations to produce this thing, and it can be done in real time. So here's an example which shows just what can be done. Here is a measurement signal. This is real data where we have, this is the signal I want to look at. This is at 2 megahertz, 2 million hertz exactly. And I want to read this, and it's at about 10 millivolts. But unfortunately, at 2,000,001 hertz, there is a signal with 1 volt amplitude. This is noise, and I want to get this. Okay? Very, very difficult problem. Now, with PRISM signal processing, I can instantly create a filter with a central frequency of 2 megahertz and a bandpass of only 0.1 hertz. And I can, well, we'll see the result. Oh, I've got it here. Whoops, going the wrong way. So that's the raw signal. This is the filtered signal. And I'll just show the two together. So what I'm able to do here is, this is the raw signal. I keep the thing that I want. I completely eliminate what I don't want. And the noise floor has been pushed down by 2 orders of magnitude. And that's with a filter that has been done using PRISM signal processing. And not only can we do this, but it's easy. You can just create a filter like this immediately. Going the wrong way again. Now, that's not theory. This is something we've done in real time, just using an FPGA. So this is the card we used for doing this implementation. So it's a commercial card, but the core calculation is just done on a single FPGA. And if we do some sums here, this FPGA implementation is doing the updates at 10 megahertz. The filter length, the whole filter length is 192 million samples to get that filter. And so that comes out as, if you were to do the calculation in the conventional FIR way, that would be 3,840 teraflops, that's floating point operations per second. So that's about 3 million laptops. Now, SUSU has a wonderful supercomputer here, okay, and its peak performance is only 473 teraflops per second. So, if you were to do this filtering in the conventional FIR way, you would need 8 SUSU Tornado supercomputers to do the calculation that we can do on an FPGA in real time. But it's not only the fact that that calculation can be done, the design is instant. So we can do another filter in 2 seconds and another filter in another 2 seconds. So the power of this technique is extremely high. Okay. Now, because you can do this filtering at any frequency you like, it's also possible to do spectral analysis using PRISM signal processing. This is conventional FFT of a, I'm sorry, I need to keep an eye on the time. When I get enthusiastic, I start talking for too long. So this is the FFT, this is conventional FFT data. This happens to be from a Coriolis meter. And we can do the same analysis using PRISM, and we get results like this. Okay, so this is the same data analysed using PRISM, and what you see is the peaks are much narrower, the noise floor is much lower, many more features have emerged, okay? And that's using exactly the same data set, so we've gone from that to that, okay? But furthermore, unlike FFT, we don't need to do the data analysis on all of the data points. We can just pick out some key areas where we want to do detailed analysis, or we can leave out the noise floor completely and just focus in on the frequencies that we're interested in. Okay, so a very powerful technique. Okay, how have we used this, and how have we used this in applications here in Chelyabinsk? two very brief views of two applications. One is pressure sensor monitoring. So what's going on here is we're interested in validating the behavior of a pressure sensor which is positioned inside of some housing to protect it from the industrial environment, where mechanical changes in the housing cause faults. And what has been developed here at SUSU is the embedding an ultrasonic transducer inside the housing to produce regular pings in order to identify whether faults have occurred. And so you get pressure signals like this that need to be, ultrasonic pulses like this that need to be analysed in order to detect faults. So if you look at that signal in more detail, what you have is multiple modes of vibration inside of the housing, where each one of these decays over time, and where amplitude, frequency, and decay information provides diagnostics. So what we've been doing is applying PRISM signal processing, the bandpass filtering I was talking about. So we can bandpass that signal to extract only one component, and this is a much, much cleaner signal from which we can extract frequency and amplitude and decay information like this. So we can now extract the diagnostic information in terms of the behaviour in frequency and the behaviour in terms of amplitude and the decay in real time. Well, we will do it in real time based on that frequency pulse and based on PRISM signal processing. Now, we could go into more details on this now, but there was a paper given yesterday at this conference by Oleg who explains this. So if you're interested in this particular application, there's more information available in the paper. And then the second application is rotating machinery condition monitoring. This work was carried out by Vladimir Sinistin. What he has developed is a wireless acceleration sensor, which is very much in the spirit of the Internet of Things, so that instead of conventional mounting of fixed sensors on the rotating machinery, instead we've got a wireless power and wireless communications device that can sit directly on the rotating part, so that the analysis is much better. So this is the device that Vladimir developed. So you have a series of accelerators, you've got the processor, you've got communications, and the system is capable of power, a wireless power communication as well. Though we've used it in a battery mode as well. So here you can see it being mounted on the rotating system, and the kind of signals that it generates are like these. And again, very interesting spectra with lots of peaks, which depends, each of these peaks is a function of the rotating speed. So the particular signal processing challenge here is you have multiple harmonics that you want to track in order to diagnose faults. But during startup, the frequencies is changing rapidly, and the system then settles at a steady speed, but at the start, you don't know what the frequency is. So we've developed a PRISM-based system for tracking just the highest harmonic during startup, and then once you identify what the steady speed is, then you can create PRISM networks instantly to track around the current operating frequency. So there's that flexibility of filter design. In a particular type of fault mode is gear faults, where if you have a worn tooth or a broken tooth, this changes the characteristics, which we can now detect using this system mounted on the gearbox. And again, very quickly here, this is real data. These are the behaviour in real time. This is in seconds of various harmonics of the amplitudes of the various harmonics. What's interesting is how they vary with time, and when the faults occur, what you end up with is it turns out that the best way of detecting gear faults is to look at the amplitude of modulation of the amplitude of the fourth harmonic. Okay? When you've no gear fault, there's low-level variation, and then as the faults get worse, you get a bigger variation in this amplitude. So with PRISM signal processing, what we can do is we can create a network of analysis. So we take the sensor data, bandpass filter, extract amplitude and frequency, and then apply the same kind of analysis again to the amplitude signal emerging in order to calculate the amplitude of the amplitude, as it were. And so we end up with a nice separation like this, whereby the fault-free case has a low amplitude of modulation, and the chipped tooth has a medium level of amplitude, and the broken tooth has a very high amplitude. And so we're able to separate out these various faults through a cascaded series of prisms and a flexible fault detection system using PRISM signal analysis. Okay. So just to summarise what we've looked at. So the Internet of Things brings many metrological challenges. PRISM signal processing is a new technique which offers solutions with low design and computational cost, very flexible toolkit for signal processing. New networks can be created in real time, and so that gives us a powerful tool set for fault detection and condition monitoring. And future collaboration between Southern Ural State University and Oxford will continue based around these themes. So thank you very much for your time and attention.